All right, in this example on work and energy, again, power will be done at a later video. We're going to look at the inclined plane. We have an object, let's say mass 5 kilograms, being pushed up an inclined plane of 30 degrees with a force of 100 newtons over a distance of 20 meters. And in this case, there's no friction. So what's going on here? Well, we're doing work because we're going to push with a force over distance d, so there's work done. And that work will then result in energy being given to this object. Now, since the object is gaining height and assuming gaining speed, then that work will then be given to the object in terms of potential and kinetic energy. So some of that work will be used to give the object potential energy, and some of the work will be used to give it kinetic energy. And of course, there will be none left over. All of it will be used for either one or the other. So what we could do here is figure out how much work is done. We have a force, we know what the distance is, so we can calculate the work done. Work done by definition is equal to force times distance. They're both vector quantities, so we use the dot product. Notice that the displacement and the force are pointing in the same direction, so the angle between them is 0, because you know that this is equal to F times D times the cosine of the angle between them, which is 1, so we don't have to worry about that. So this is going to be 100 newtons times 20 meters, or 2,000 Newton meters, which is 2,000 joules of work. So that's how much work the force did on the block. Let's figure out how much of that work is used to give it potential energy. If we now draw a triangle here, we can see that this is the height gained h. And if we're going to calculate h is equal to the hypotenuse times the sine of the angle theta, because h is opposite to the angle. Of course, this is also the angle of theta, 30 degrees. The distance, 20 meters, is along the hypotenuse. So this is equal to 20 meters times the sine of 30 degrees, which is, of course, sine of 30 degrees is 1/2. And 1/2 times 20 meters is 10 meters. So 10 meters of height was gained, which means we can now calculate the potential energy of the block when it's reached a distance of 20 meters of the incline. So the potential energy, which is calculated by saying mgh, that's equal to the mass of 5 kilograms times g of 9.8 meters per second squared times the height of 10 meters. So that's 5 times that is 49 times 10 is 490. So potential energy is equal to 490 joules. All right, so we did 2,000 joules of work. 490 joules was used to give the block potential energy by rising it up 10 meters. That means the remainder, the kinetic energy, will be equal to the work done minus the potential energy, which in this case will be 2,000 joules minus 490 joules, which is equal to 1,510 joules. Now, could we have figured out the kinetic energy in another way? Well, yes, we can say that kinetic energy is equal to 1/2 mv squared. So if we somehow figured out how much velocity the object had, knowing the mass, we could also have figured out the kinetic energy. So, can we figure out how much velocity the object will have? Well, we can use the equation F equals ma, and of course that needs to be F net equals ma to calculate the acceleration. And then we can use the equation v squared equals v initial squared plus 2ax, x being, of course, along the slope of the incline. Once we know the acceleration, we know the distance, the initial velocity is 0, we can find the final velocity and therefore also find the kinetic energy that way. So let's do that. So to find the net force, we have to look at all the forces acting on the block. So we have mg pulling down, which can be divided into the vertical and horizontal components. So this would be mg cosine theta, and this would be mg sine theta. So the net force will be 100 newtons minus mg sine theta. So calculating the acceleration that way, we can say that the acceleration is equal to F net divided by the mass of the block. So F net will be the 100 Newton force applied to the block minus the mg sine theta, all divided by the mass. And so this will be 100 newtons minus the mass, which is 5 kilograms, times g, which is 9.8 meters per second squared, times the sine of 30 degrees, which is 1/2, and take the whole thing and divide it by 5 kilograms. Of course, that would be 45 times 1/2, 49, that would be 24.5. So this is 100 newtons minus 24.5 newtons divided by 5 kilograms. And so this is equal to 75.5 newtons divided by 5 kilograms. And so that goes in there 15.1 times, 15.1 meters per second square. Let me check that real quick, because I didn't use my calculator and I make mistakes sometimes. So that's 49. Half of 49 is 24.5. And that looks about right. Okay, so now that we know the acceleration, we can come over here. And so we can now say that v is equal to the square root of 2ax, because v initial, that will go to 0. So this is equal to the square root of 2 times what we just found, 15.1 meter per second squared, times the distance of 20 meters. And let's find out the velocity. Matter of fact, we don't even have to take the square root, because then eventually we'll want to put it back in here, but makes it a little bit more comprehensible. 15.1 times 20 times 2, take the square root, is 24.58, roughly speaking. So this is equal to 24.58 meters per second. We plug that in here, multiply times 5, and multiply times 1/2. So it's 1/2 times the mass times 24.58 meters per second quantity squared. And let's see if we get the right kinetic energy here. So we square that, multiplied times 5, divided by 2 equals, and I get 1,510 joules, which of course is the amount that we predicted on that logic right there. So you can see that we can find the kinetic energy in 2 ways. We can calculate the potential energy first, subtract it from the work done to get the remainder energy, which therefore must be kinetic energy, because none of it was lost due to friction. And then instead, we can also find the acceleration using Newton's second law principles, then plug that back into our equation of kinematics that doesn't require time, find the velocity, plug into our equation 1/2 mv squared, and we get the exact same number. Again, of course, this is easier to do, but it's good to see that you can do it both ways to get the full understanding of how this works.